month ago, as we were walking to get ice cream, my teenage son declared, "The brain is weird." I was a bit taken aback because I study the brain for my profession. He continued, "It's weird because it's the only object that has named itself." Well, he had me there. The brain is weird, weird in a very special kind of way. And it's this special ability of the brain to name itself and to transform who we become as individuals and as a species that I want to focus on today. For starters, consider that the human brain, with its 86 billion neurons, has a tremendous ability to represent and process information. But unlike computers, where the advances in computing power have been driven by improvements in the technology that's used to build them, the computing power of the human brain rests upon biological hardware, hardware that's thought to be essentially unchanged for tens of thousands of years. So this means something really interesting. It means that the tremendous achievements of humankind have occurred because of improvements in our cultural software, knowing how to program and to use our brains, rather than by changes in our innate abilities. So put another way, this suggests that if we could travel back in time 30,000 years, we could teach a caveman to read. This perspective on the human brain interests me deeply because I'm interested in reading, a powerful but culturally recent innovation that has to be acquired using a biologically old brain. How exactly do we do that? Well, over the past 20 years, researchers have learned a lot about the brain and language. And one thing that they've learned is that there is a particular region of the brain called the visual word form area, or VWFA for short. It's about the size of a sugar cube. When a person learns to read, when they acquire literacy, they transform this piece of their brain into a critical region that supports reading. It's due to your VWFA that each and every one of you are fluent and skilled readers. If you have the misfortune to have damage to your VWFA, such as might occur through a stroke, you will lose this ability. You will find that reading becomes effortful and you have to recognize a word letter by letter. In the words of the neurologist who first described this problem, you'll exhibit word blindness, even though your ability to recognize all kinds of other visual objects can remain intact. We've learned a lot about the VWFA, but we still don't fully understand what makes this area so special for reading and how does it become specialized. But we're making progress, and what we're learning is giving us new insights into this special ability of the human brain, this special weirdness, if you will. One of the research tools that is available involves patients with intractable epilepsy who are scheduled for surgery to remove the brain tissue that is causing their seizures. As a part of pre-surgical planning, these individuals have electrodes placed on or into their brain so that the origin of their seizure can best be localized. While they're in the hospital for this procedure, they often volunteer for research. And I've become part of a cross-collaborative team, a research team, that's working with these very special and dedicated volunteers. One of these volunteers, who I'll refer to as KT, had an electrode placed directly into his VWFA. This gave us a really unique opportunity to study the VWFA in action. One of the things that we did is we asked KT to read while at the same time we delivered small pulses of electricity to different electrode sites. These pulses of electricity essentially sort of short-circuit the normal electrical activity of the neurons causing the stimulated site to become temporarily dysfunctional. In the video that I'm going to show you, you'll see KT reading letters and words without stimulation to his VWFA. And then you'll see his error-prone performance with stimulation. In essence, we created a temporary reading disorder. Now, it may not seem that dramatic as you watch, but think about it as you're watching. If you had problems, or if you confused even a small percentage of the letters and words on a printed page, think about how challenging that would make reading.
R, pencil. F, H, nature.
Now, in addition to stimulating through those brain electrodes, it's also possible to use them to record the local neural activity. This gave us the opportunity to measure the temporal dynamics of word recognition in the VWFA for the first time. One of the questions we asked is, how quickly can the neurons in this region discriminate between a word and other kinds of visual objects? And the answer is very quickly. It only takes about 0.2 of a second. But we also asked a more important question. And that question is there a different pattern of neural activity in the VWFA for different printed words? If so, this would suggest the VWFA contains something like a mental dictionary with a different entry for each printed word that a reader knows. To our excitement, we found evidence for such a mental dictionary. We found that about 1/10 of a second after you could examine the neural activity in the VWFA to tell whether or not KT was looking at a word, we could tell which word KT was looking at. These results are consistent with a long-standing theory in the psychological literature, which holds that recognizing a printed word involves an aha kind of moment in which you need to take representations of the visual form of the word and bind them together with representations of how the word sounds, its name, and its meaning. And when this binding is successful, then you achieve conscious recognition of the printed word, and you're able to individuate it from all of the other words that you know. We think that we're seeing the electrical signature of this binding process in the VWFA, and that through its unique properties, it's able to have a unique pattern of electrical activity to represent each unique word of the roughly 25,000 that are known by an adult reader. So how does this specialization happen? And what makes this particular area of the brain so important? Some researchers think that the location of the VWFA is determined by the fact that printed words all tend to look the same, even across other kinds of written languages. And so this similarity in how words look will cause words to land, if you will, in the same piece of the visual brain. But we favor an alternative idea, which is the location of the VWFA is driven by its need to connect, its need to form connections to those brain areas that represent the sound and meaning of spoken words. This idea predicts that any kind of visual form could be used as the letters in an alphabet, and the VWFA would still be recruited for reading. In other words, it's not the forms that are important, it's what you do with them. To test this idea, we developed an artificial alphabet that we call the Fiez font alphabet, and we taught it to college students. In our Fiez font system, each of the 35 consonant and vowel sounds of the English language is mapped to a specific face. On the first day of training, subjects learn the letter-sound correspondences, and then they spend the rest of the week learning to sound out English words that are spelled with these Fiez letters. By the end of the second week, our readers are able to read a simple story printed in face font at about the level of a first grade reader, as you'll hear in this audio clip.
Irma loved to dance. Irma loved to dance by the birch trees.
Having now trained our subjects to read face font, we were able to use another method, functional magnetic resonance imaging, to answer the following question. Now that we've created a new kind of literacy, have we created a new kind of VWFA? A VWFA that regards it as perfectly legitimate to put together a string of faces as a way to print an English word. Using this technology, we showed face font words to a group of subjects who had acquired face font literacy. What we found is increased signal in the VWFA, as indicated by the blue bar. Moreover, we found that the best face font readers exhibited the strongest activation in the VWFA. For participants who had not learned face font, we didn't see changes in the VWFA. This is what we would have expected because the specialization of the VWFA requires reading experience. But there's something magical about this experience. We think that the VWFA is able to use this experience to train itself. This self-training of the VWFA, we think, hinges upon a cultural innovation. About 8,000 years ago, humans had conceived of the idea of using characters to represent word meanings. And this idea evolved, and about 5,000 years ago, there were written systems in which some of the symbols represented words and others represented pure sounds, like the syllable that might be part of a person's name. But about 3,000 years ago, there was a singular innovation. It was the idea of using symbols to represent the basic sound elements of spoken words, the consonant and vowel sounds. And that by having a small set of these symbols, a small set of letters, one could use them and combine them in all the ways that were necessary to represent any spoken word. This gives readers of an alphabetic system the ability to teach themselves how to read once they master the basic alphabetic principle. The idea is really quite simple, and our work with face font is allowing us to understand its brain basis. It goes something like this. When a reader sees a word they don't know, they can use their knowledge of letter-sound correspondences to sound out the word. We think that this sounding out process makes use of a region in the front part of the brain that is involved in overt speech production, but importantly is also involved in an inner speech system, so that by saying the sound of a letter's name, either out loud or just silently to yourself, you can activate the sound areas of your brain as if your ears had actually heard it. By repeating this process through the set of letters in a word, you can create the component sounds that comprise the word. And then you have the opportunity for discovery. You have the opportunity to take these sound segments and blend them together. K, at, cat. And when you discover what this printed word is, when you recognize it, you allow your VWFA neurons to become connected to the neurons that represent the word sound and meaning. With practice, these connections become stronger, and eventually, a reader is able to look at a learned, familiar word and without effort, automatically activate the interconnected form, sound, and meaning neurons. The next video shows this training in action. I think it does a great job of highlighting the idea that learning requires speech production and not just looking at words. And it's a wonderful example of how culture helps us learn how to use our brains to give us those programming tools that the brain needs to shape itself.
Umbrella.
So try to think what word sounds like that.
Tiger.
No.
Umbrella.
Umbrella! Amazing.
So I'll leave you with this. When we combine the tremendous biological hardware of the human brain with the human drive towards creativity, innovation, and adaptation, amazing, unpredictable, and somewhat weird things happen. Thank you.